Okay, a model of competing species. So what we have for competing species is that we have two species, X and Y, right? I don't know what they are. Suppose they're, I don't know, moose and elk, right? Two species that eat the same thing. We'll assume that encounters between species are bad for both species, and both species, if the other didn't exist, would follow a logistic model. So here's our example. X is one kind of animal, Y is another kind of animal. So for X and Y, A and C are growth rates. M and N are the environmental capacity or the carrying capacity. And B and D are the costs of encounters. So what's going on here? So for the population X, if Y was zero, if there were no Y animals, then dx dt is a logistic term, 1 minus x over n. And if you think of its phase line, it would have an equilibrium at 0, an equilibrium at n. Population would decrease. So n is a stable amount. Population increases. If you start between 0 and n, population would increase to n. If you start more than n, population decreases to n. Not really worried about what happens physically if x is less than 0, but if you have negative animals, the population decreases there as well. So n is the carrying capacity. It's how many of this species X you would have if there were no Y. And Y is sort of set up the same way. It's got a growth rate, which is C, and a carrying capacity of M. If there was no X's, nothing would happen. So interactions, generally we model that by xy. If x is the number of one species and y is the number of the other species, then x times y is the number of ways any one x animal can meet any one y animal, right? If there were two x's and three y's, then there'll be 6 ways that those animals could interact. And then b and d are the costs of the encounters. B is how much it costs the X animals, is the rate of change for the X animals when they meet the Y animals. D is the rate of change for the Y animals. And we're assuming A, C, N, and M, B, and D are all positive numbers. And so that's what the model is. Basically, you have two animals, each of which have their own natural population, but they compete with each other, and so encounters between them are bad for both. An encounter could mean basically the elk came along and ate all the food off of a tree, and then the moose came along and was like, oh my god, there's no food on the tree left because the elk came and ate it. And so that's what we're talking about when we're talking about encounters. So here's an example with concrete numbers. dx equals 12x, 1 minus x over 12 minus xy. This population has a stable population of 12. This population is a stable population of 18. This one grows faster than the others. I chose the numbers there because it just made the calculation easier. But the Y population is harmed more than the X population by encounters. So how do you go about graphing this? Well, this is what we did in the previous section, right? You find the equilibria, you linearize at the equilibria, find the null lines in the direction of the vector fields along the null lines, and sketch the vector field. So instead of doing all the details, I'll just give you the results. There's 4 equilibria, 0, 0, 0, 18, 12, 0, 3, 9. The 0, 0 is a source because you've got two positive eigenvalues. 0, 18 is a sink because there's two negative eigenvalues. 12, 0 is also a sink because there's two negative eigenvalues. And so note that what those three mean is that if you start with very few animals of both types, both animals just populations increase. If you have 18 of the Y animals, right, and that's the, if you're near to that stable population, what happens is that you have a sink, and so that means you tend to having 18 animals, Y animals. All the X animals die out. And same thing happens for when X is near to 12. If you're close to the equilibrium number for the X animals, then since you're near a sink, you'll tend to the sink, and that means that you'll end up with um, you'll end up with 12 X animals but no Y animals. 3,9 is an equilibrium, but you've got one negative and one positive equilibrium, so you have a saddle. You tend in towards it on one way and then out along the other way. And then you can find the null clines for x prime of t equals 0, right? X equals 0 and x plus y equals 12. And so we find the sign of the y component pointing up and down, and the null clines for y of t, y equals 0, 3x plus y equals 18. You can find the signs for those. Okay, so what's a sketch of the graph of our thing looking like if we put all that together? Oh, having a little trouble with my tablet. There we go. There's an y-axis and an x-axis. Let me actually redraw that. There. I'm going to put actually, I'll redraw that as well. Going to put this more like this because we're not really interested in anything but the first quadrant, because the first quadrant is where our animals, where we positive animals. So what have we got here? If we're looking at the linearizations, well, let's start with the null clines, and then we can add the linearizations there. So the null clines for x, or the y-axis, that's one null cline. Well, sorry. The very first thing we put in, of course, are the equilibria, right? And so we have an equilibrium at 0, 0. We have an equilibrium at 18, 0. We have an equilibrium at 12, 0. And I'm putting the numbers far enough away that so that I can draw in some pictures. And this one over here, it's 3, 9. And that's this equilibrium. Okay, so now, right, that's the null cline for x prime equals 0. So if there's no x animals, we expect to have a logistic kind of phase line here for the y animals. They just end up with 18. Likewise, the null cline for y is the x-axis, and that gives me this. My animals end up at 12, 0 if we start with no y animals. And so note, of course, that these are 1, equilibrium is 2, 3, equilibrium is 4, 5 solutions here on the x-axis, and 1 equilibrium, 2, 3, and 4. So those are our equilibria. And note, each quadrant is sealed off from the other quadrants. Whatever solutions, if you start in one quadrant, you all stay in that quadrant. So the other null clines is we have a null cline for x that runs through this. This is the line x plus y equals 12. And along this, we have y going up here, and then y goes down here, and y is up here. Right? And that's, if we go up here, right, that's this null cline with this kind of information on it. And the other null cline we have is, this is an x prime equals 0 null cline. Then we have a y prime equals 0 null cline that goes through here. And The solutions for the nullines the arrows look like this. Right, and so our equilibria are all at intersections of an x prime and a y prime nullline. So that gives us a little sense of where things are going. Things should be coming down like this, right? You can sort of see where the arrows are pointing. And then we want to know what's going on at the equilibria. So at 0, 0, we have two eigenvalues, both positive, and our eigendirections are like that. They look a little bit like that, because along the x-axis is the smaller of the two eigenvectors. At 0, 18, we have, it's up here, the y-axis is one eigendirection. Then we have another eigendirection that lies in between the y-axis and this nullline going in. I'm not going to add any more curves there because it's getting a little bit complicated. Down at 12, 0, the x-axis is an eigendirection, and then there's another eigendirection that's going in that looks something like that. And then this one is a saddle with a direction going in like that, and a direction going out like that. So this arrow should be in between those two nullines. So what's going on here? Well, saddles are always interesting because you can get some interesting separatrices here. There should be something that starts here and then just goes up and runs in there. And likewise, there should be another one that comes out there. This one really has no place to go, right? This curve, everything points in. This curve, everything points up. And this curve you can't cross because it's a solution. So this solution is trapped in this triangle, and it's got to go up to that sink up there. Likewise, this solution is trapped inside of this triangle, right? This is a solution. This is a Lyapunov curve. This is also a Lyapunov curve. Everything that enters into this triangle is trapped in it, and in fact, has to go down to there. So if we start out here on this side of this thing, it would come down into here and over there. If I started over here, I would come down into here and up there. If I started out here, you would come up, cross this, and up to that one. Here you come up, cross this, and down to that one. So pretty much everything over here will go to this one. Pretty much everything over here goes to this one. The only way you could actually end up at this equilibrium is if you started it on it, or if you started on these separatrices that actually run straight into it. So let me, below here, just draw a sketch of the separatrices alone. The x and y axes are separatrices. We have equilibrium up here, an equilibrium here, and an equilibrium down here, and an equilibrium here. We have one solution that runs up to there. We have one solution that runs down to there. We have one solution that runs up like that, and we have one solution that runs out like that. So there's sort of four regions where our animals can start. Anything in this region or in this region, you'll end up going to that, which means the X animals die out. Anything in this region or this region goes to that equilibrium, which means that the Y animals die out. One of the things you'd like to look at if you were actually dealing with this model is what's the ratio of the sizes between this area and this area. What percentage of starting conditions give you X animals as an end result? What percentage give you Y animals as an end result? And that is an analysis that's a little too complicated, but we could certainly, but people certainly do that. So the fate of the animals. Oh, we're actually not going to go to Excel. You could if you wanted, but won't. One or the other dies out since these are the only stable solutions. Okay, so if we go to GeoGebra, so we'll stop that share and we will share instead GeoGebra. So here's all the commands that I did. This is the same set of commands that I did for the previous example. So we can shrink this in a little bit. There is our slope field, right? And you can see, right, kind of what it looks like there. Equilibria, right? Those are 4 equilibria. Right? These are 2 are going to be the attractors at 18 and 12. So what are our nullines? The nullines for x with those 2, right? And so this is all solutions, and this is things, vectors pointing up or down, and these were the nullines for y, right? Vectors pointing left and right. So this triangle here, this purple line is actually a solution, so you can't cross this. Here, arrows are pointing up. This red curve, arrows are pointing left. So if you enter this triangle, you end up here. Likewise, this triangle down here, this red curve on the x-axis is actually a solution. On this purple segment, arrows are pointing down. On the red segment, arrows are pointing to the right. If you enter this, you end up at 12. So what kind of solutions can we get? Let's see. There's roughly where that separatrice is. And I got that basically by, you take the eigenvector and you add it to the point, right? You just figure out, here's the point, and there's an eigenvector, and you just add that to that point and just try and run the solution through there. And likewise, that's the other eigensolution. So everything on the left here of this black curve goes to 18 y's and no x's. Everything to the right goes to 12 y's and no x's. This has got a slope of about 4, so I would guess maybe 25% of initial conditions go to y's, but that's just a guess. And we can try and look at the other 2, right? These are the other separatrices. So if we turn off the nullines, we get that as our solution curves. Maybe want to keep these 2, right? Red is a solution curve, purple is a solution curve, and the black curves are solution curves. And so you can see everything will either end up over here at 12 or end up over here at 18, depending on where you chose to start your solutions. And we can read off what the behavior of the animals are from that. So that is a competing species model in which one or the other of the species goes extinct.